So what are eigenvectors? And we're going to look at the finite dimensional vector space, and we're going to look at square matrices. And square matrices can be characterized by their eigenvectors. So let's explore this concept. So here's a matrix, a square matrix, and we're going to think of it as an input and a transformation. So there's going to be an input to that matrix, and the matrix is going to perform a transformation on the input vector. So here's an example. And the multiplication of this matrix with this vector gives us this vector. So let's think of that as an input vector to a transformation, and this is the output vector. Now, what can we notice about this particular example that we've shown here? Well, one thing that we can notice is that if we were to plot this vector on a grid that is orthogonal, so here's a grid here, then the slope of this vector would be 1/5 horizontal and then 4/5 vertical. So the slope here is 4 up to 1 across. Okay, so that's, I might write here, slope 4 to 1. Now, what about the output vector? The output vector has a slope of 2 to 1 because 3.6 is double 1.8. So in this case, this transformation from this vector using this matrix, the matrix has transformed it from a vector with a slope of 4 to 1 to a vector with a slope of 2 to 1. So let me just plot these here on this curve here. So this means this one here from 1.8 and 3.6 is the output. So here's 1.8. It's going to go up to that point there, but not all the way because it's not 2 to 4. So 1.8 and 3.6 is that vector there. This is the output vector. And the input vector was 1 to 4. So that's going to go along this line here, but of course not all the way. It's 1/5 across and 4/5 up. So this is the input vector here, and this is the output vector here. So what we can see here is that this transformation on this vector has involved a rotation and a scaling. So this vector got rotated and scaled. So I'm going to write that here, rotation and scaling. Okay, now let's look at another example and try to get to an idea of what these eigenvectors are. So here's another example. It's the same matrix doing the same transform, but now we've got a different input vector. This is 2/3, 2/3. And the output now is 4, 4. So in this case, the output vector is this vector here, and the input vector is in the same direction. So the slope has not changed. There has not been a rotation because the input is 2/3, 2/3. So that's this vector here is the input vector. So now we've got the input vector and the output vector in this example here, where the only thing that's happened is a scaling. And actually, this is an eigenvector. So here's our equation for an eigenvector. It's if you have the vector, you multiply by the matrix, which is the transform, and if the output is just a scaled version of the input vector, then that vector is an eigenvector. That's the definition. So for some people, this is the answer that they're looking for. And this is true. And for some people, that's enough intuition, that the fact that vectors that don't rotate are eigenvectors. But I have a number of other questions in my mind. I'd like to know more intuition. I'd like to know, do they always exist? Have I just simply chosen a matrix here which has this special property that in some directions the vectors don't do a rotation? Is it more general, or have I only done a specific example? Also, what do eigenvectors tell you about the transformation? Do they tell you something that's other than simply the fact that one particular direction doesn't rotate? And also, how can you relate different transforms? So how can you compare different matrices? Can you use eigenvectors to help you compare different matrices? And the answer is yes to all of those things. So let's, instead of think of it in a different way, instead of thinking of it as moving a point or changing a vector, so moving from a point here up to a point there, let's think about it in the other perspective. So let's fix the point and think about changing the basis vectors. And that's what I prefer to do to get more intuition. So let's think of another example where we're going to do this, as I said, the opposite situation. So let's think of a situation here. Maybe let's think of an example. So maybe you've got north direction and the east direction, but let's think if you've only got two roads that you can drive along. So let's say there's a house located at a certain point, and you can only observe that house by driving along these roads. So let's say you can't drive along a road going due east or a road due north. Those roads don't exist. You can only drive on these roads here. Let's take that particular example. So what you could do is drive along this road. You could start with your car and you could remember what that angle is, and you could drive along this road here, looking at that angle until you get to a point where you can see that house. So let's say we did that. So let's say we drove along this road, looking at that particular angle until we got a distance along that road where we could see the house. And we could measure that distance. So let's say, for example, this road here had this exact length. I'm going to represent it with a vector here, but let's say this is the length of the actual road. I'm going to call it the vector W1. Okay, now let's say we knew the length of that road, and let's say along the road there were road signs telling us what fraction of the total distance we had travelled. And so here we would know that we've travelled, let me call that a C, a distance C, which is a fraction. That is a fraction of the total distance of W1. That's what we're going to do. Now we drive back, and we'd like to look at it from the other direction as well. And so we're going to drive out along this road, looking in the direction of W1. So let's drive along this road until we can see the house in the direction of W1. And we're going to call that there a distance D. Again, let's call this W2, and let's say that road has exactly that length. And then we've got road signs that tell us what fraction we are along that road, and we're going to call that distance D. So now we've got it in terms of W1 and W2, but we'd like it in terms of east and north. So we need to do a change of basis. So let me define two other vectors. I'll call this U1 here, which is a unit length in the direction of east, and another vector U2, which is a vector of unit length in the direction north. So now we need to do a change of basis from W1, W2 into U1 and U2. So here we have two equations, or let me start with this equation first. Here we have an equation for W1 in terms of U1 and U2. So in this case, I'm just using general M and N, but we can see in the example I've drawn, there's 1, 2, 3, 4, 5. So M would equal 5 and N would equal 1, 2. We've gone up 2 units in the direction of U2. So we have this equation here. So I'm just going to draw this over here on the side here, just for our, in the particular case of this, so we can remember this. So we've got M equals 5 and N equals 2 in this particular example. And then we also have another equation for W2. So W2 is this vector here. It can be written in terms of these new east and west basis vectors by PU1 plus QU2. And in the case that I've drawn here, the P equals 1 and the Q equals 4 in this case. So they just use an example here for the particular case that I've drawn. But this is the general case. Now let's write this in terms of, to do this change of basis, let's write this in terms of a matrix. So now we can write W1 in terms of the vector U1 and vector U2 stacked as columns in a matrix. And then we're multiplying this by the vector Mn. So U1 would equal 1, 0, and U2 would equal 0, 1. That's those vectors. And we can write that as a matrix times Mn. And we can do the same for W2. Okay, so we've now got this with the vectors U1 and U2. So we're changing from the W basis to the U basis. So we've got a house, and we've got that, let's call that a vector X. So I'm going to draw that house there with a vector X. And now we've measured it in the other basis, but we'd like to, of course, change the basis. So now we can write an equation for X. And x equals c times w1 plus d times w2. That's what we could measure there. Those were the fractions of w1 and fractions of w2. Again, just as we did for up here, we can write that in terms of a matrix. So we put the vector w1 and the vector w2 times cd. So now we've got a matrix times a vector. Now let's use these equations and we can change from this into the basis of u1 and u2. I just move the camera down to do this and reveal this line here. Okay, so now we've got, we can write w1 using this, exactly just substituting these two expressions here into this expression here. We can rewrite x in terms of u1 and u2. And it now comes, you can confirm it for yourself, it equals a matrix with these elements, these mn, p, and q elements, times c and d. And then this matrix times a vector gives us a vector. So again, we can think of that as the input. So here's what we're doing. We're thinking of the input as the c and d, what we've measured, the fraction in the original basis. And now we can multiply it by this transform matrix to get the fractions in the new basis. Okay, so here's where we're coming back to eigenvectors. Okay, to try to understand eigenvectors. Here's where we have the transform now, the taking a vector, putting it into a matrix. And we'll just take one example here, for it'll match up with the one that I've drawn here. Let's say that c equals 5 divided by 18, just to pick the example that I've drawn, and d equals 11 divided by 18. Okay, so in that case, which is the case that I've drawn here, in this case, you can substitute those into here, and you can substitute c and d into here, and you can substitute m, n, p, and q for these numbers here, and you can find out that a and b will equal 2 and 3 in the case that I've drawn. So I chose them that way just to show it and make it easy for me to draw, but in general, this holds for any m, n, p, q, c, and d, but I've drawn it this way just so that we can visualize it more easily. Okay, so as I said before, just repeating, over here on this side, we looked at this from the perspective of changing the point and seeing whether it rotated if you changed as you go through this transform. On the right-hand side, we're keeping the point fixed and we're changing the basis vectors. Okay, now why are we doing that? Now, this is where it comes to this explanation of the eigenvectors. And I think it's more informative on this side. We get more generalizations. Okay, so let's think about what we did. So here, in this case, we've gone from c and d, which were 5/18 and 11/18, into 2 and 3, once we did this change of basis. So we've gone from cd to ab. Now, the ratio of c and d, c ratio to d, is not the same as the ratio of a to b. Okay, so this is A, I'll just write it here, A equals 2, B equals 3. So the ratio has changed. And here in this perspective, it's the ratio that we're looking at. Not over here, it corresponded to rotation, but rotation is just one example of the more general ratio. So I prefer to think about ratios rather than rotations, although they are equivalent, but as I said, rotation is a special case. Let's look at ratios here. So the ratio of C to D, which is 5/18 to 11/18 in this example, is not the same as the ratio of A to B, which was 2 to 3. But there will be places on this graph where there is the same ratio maintained when you do this change of basis. And that is where the eigenvector is. So let's look at that example and see where that is. And you probably guessed by looking over here, because I've used the same matrix, if you've noticed, this 5, 1, 2, and 4 is the same as the matrix over here. So we've got the same matrix transformation on both sides. And so you've probably guessed that the transformation is that the eigenvector, in this case, is the one that's at 45 degrees. And so I'm just going to draw that line in here, and that here we have, this is 4, so this is at 45 degrees. So now let's see, why is that the case that it's 2/3 of the way along here? Because if you go parallel to this one here, and you go back from there, then you get to a vector which is 2/3 of the way along W1. And you go again parallel to this one from here, and you'll find that this is a vector which is 2/3 of the way along W2. So this one here is 2/3 of the way along W2, and this is 2/3 of the way along W1. So now we've got the case along this line, and for this exact vector here, because you come down here, you put in 2/3 and 2/3. If you drove along this road and saw that point there, if there was a house there and you saw that point there was 2/3 of the way along W1, and if you drove up this road and saw that it was 2/3 of the way along W2, then you put that into C and D, you would get answers 4 and 4 coming out and in the basis of U1 and U2. And so this is this direction here and this direction here, 4 and 4. And that's what this point here shows. So this direction is an eigenvector for this transformation of bases. And so this is where we get the more general intuition for eigenvectors. So this case has this one here, but I think now you can see to our first question about whether eigenvectors always exist, now we can see that we can generalize this much more in your mind's eye compared to the situation over with rotations, because now you can see if you change these basis vectors, then you will always be able to find this eigenvector direction. Maybe if they move further apart, the eigenvector might stay the same. If one stays fixed and the other moves down, then the eigenvector will move down. In other words, the direction where you get an equal ratio before the transformation and after the transformation, that is the eigenvector, and that will exist. The symmetry of this situation should show you, and you should be able to see in your mind's eye, that the symmetry will indicate to you that this general case here that I've drawn holds even if these vectors are drawn at different angles. So now let's think about whether this eigenvector is unique for this transform. And it turns out it's not. So let's think about points in the space which are at negatives of the points we've been thinking about so far. So if we put negative C and negative D, then instead of this point over here, we're thinking about a point down in this direction. And then you can see, I think you'll be able to see, that you can still get points which are negatives in the same ratio, and therefore this vector also continues in the negative direction. So the vector going this way and also the negative version of that vector going this way is also an eigenvector. But these are really just duplicates of the same vector with a different scaling, a negative scaling. Now it turns out there's actually another eigenvector. So let's think about if we only put a negative on one of these values. So let's say we keep C and we do a negative of D. Then in this case, we have a point that is along this direction here. We've got a positive C, but a negative D, so negative of this direction. Then we've got points that are down in this region. And now I think if you can think of some symmetry in your mind's eye, you're now going to be getting a direction in this way, which is going to have equal ratios before and after the transformation. And so there will be another eigenvector in this general direction when you consider negative values of either C or D. The negative D will be down in this region, points and the vector going this way, and the negative C will be in this direction up here. So in this case here, there will be two eigenvector directions where there is this symmetry, where you've got the same ratio before the transformation and after. One will be like this, and the other one will be somewhere over here. Now, will those eigenvector directions be orthogonal? That's probably the last thing to think about. And the answer is, in general, they will not be orthogonal, because it depends on the angle of this slope here depends on where those two vectors are. And these two vectors are not orthogonal themselves. So there's nothing actually to say that the other eigenvector direction will be orthogonal to this eigenvector direction. But there are situations when it is orthogonal, when the other eigenvector is orthogonal. And that comes about when the transform matrix is symmetric. When the transform matrix is symmetric, then these vectors have a symmetry to them such that when you multiply one of them by a negative, I think you'll be able to see, if you can imagine that in your mind's eye, or if you can put some numbers in yourself and then draw the vectors, you'll be able to see that when you take the negative of one of the vectors, it actually has a symmetry which provides a an orthogonal direction for the other eigenvector. So when you have symmetry in the matrix, in the transformation matrix, a symmetric matrix, then you do have orthogonal eigenvectors. And the final thing to say is all of this holds if the numbers are complex as well. Then instead of just having it for a symmetric matrix, it needs to be a complex conjugate symmetric matrix, or in other words, a Hermitian matrix. But everything here holds for complex numbers as well. So if this has been useful, please give the video a thumbs up. It helps others to find the video. Tell your friends about it. Check out the web link in the description below, where you'll find a full categorized listing on the web page that's listed in that web link. And of course, subscribe to the channel for more videos.